When you connect your laptop to Wi-Fi, it feels like a magic pipe instantly delivering data from the router straight into your device. That intuition is dangerous for any engineer or builder because reality works differently. The truth is that Wi-Fi is not a dedicated tunnel. It is a crowded room where every single device must shout over one another on the same frequency to be heard. For 25 years, we have been trying to solve this exact problem of how machines share air without crashing into each other. We moved from protocols that forced everyone to take turns speaking one at a time to sophisticated systems that schedule who gets the floor simultaneously. This shift is not just about faster shouting. It is fundamentally about engineering coordination in an environment where collisions are inevitable and latency spikes when traffic grows heavy. Understanding this distinction changes how you design systems, troubleshoot networks, and evaluate new hardware for your stack. The core reality of Wi-Fi stands in stark contrast to the wired connections most engineers trust implicitly. Unlike Ethernet cables, which provide a private lane per device, Wi-Fi operates on a shared radio medium spanning from 300 MHz to 300 GHz microwave spectrum. Every connected device transmits and receives via electromagnetic radiation broadcast to everyone within range. Receivers must constantly filter for matching group IDs or SSIDs while ignoring the chatter of neighbors trying to use the same space at the same time. Early Wi-Fi standards, specifically from the original 802.11b era, established in the late 90s, relied on what engineers call distributed coordination functions. In this model, only one device could speak at a time across an entire network segment. If 10 devices were connected to that single access point and all tried to send data simultaneously, they would queue up, wait for silence, transmit their packet, then wait again. This created severe saturation under load where adding more users actually slowed everyone down rather than increasing capacity. The engineering landscape shifted dramatically around 2014 with the introduction of Wi-Fi 5 and later Wi-Fi 6, which shattered that one user at a time paradigm through technologies like OFDMA and MU-MIMO. These innovations allow multiple devices to transmit simultaneously by dividing available spectrum into smaller subchannels or utilizing different spatial streams on antennas. The speed gains we celebrate today are not just about hardware shouting faster. They are the result of software-defined scheduling that coordinates concurrent transmissions across a chaotic radio environment. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This distinction is critical for system design because treating Wi-Fi like a wired pipe leads to catastrophic failures in production environments. Research into campus-wide networks identifies channel overlapping and network saturation as primary failure points when too many devices compete for airtime. This results in packet collisions, queuing delays that manifest as lag, and dropped connections, phenomena that simply do not occur on dedicated wired links under similar loads. You must engineer for contention rather than just theoretical bandwidth, because a high-speed access point will still fail if it cannot coordinate concurrent transmissions effectively. When latency spikes during troubleshooting, the instinct is to assume the router hardware has broken in the traditional sense. In reality, the device is likely experiencing radio contention, where signals bounce off objects creating unique interference patterns that degrade performance. The solution often requires reducing device density on a single access point or moving to higher frequency bands like 5 GHz and 6 GHz where channel overlap is less severe than the crowded 2.4 GHz band. Data rates have increased by over 1,000 times from the original standard not just through faster hardware, but by aggregating spectrum across these three distinct frequency bands, 2.4, 5, and 6 GHz. Beyond data transport, modern Wi-Fi signals are dynamic environments that carry far more information than payload bits alone. Deep learning models now treat radio waves as sensory input to detect human activity such as walking or falling without the need for cameras. This capability proves that the medium itself can be a sensor input via channel state information analysis, but introduces noise and variability that requires robust signal processing or machine learning models to interpret correctly. If you are building IoT systems, understanding this dual nature of Wi-Fi is essential because it means your network infrastructure might also serve as an environmental monitoring layer for your applications. The career relevance here touches on the fundamental judgment calls every practitioner must make regarding trade-offs and adoption strategies. For system designers, stop designing for theoretical maximum throughput which never exists in practice. You must design for airtime fairness, where a network with high theoretical speed fails if access points cannot manage channel overlap effectively under load. This means prioritizing coordination protocols over raw frequency increases when planning infrastructure that will face real-world congestion. For AI and data engineers, the implication is that Wi-Fi signals are carriers of both bits and environmental context simultaneously. If you integrate radio sensing into your architecture, you must account for the fact that walls, furniture, and human movement alter signal propagation in ways that require continuous calibration. The speed trajectory over 25 years shows aggregate spectrum usage, enabling massive gains through better coordination rather than just raw frequency increases. This reinforces why understanding the engineering behind the hardware is more valuable than knowing the marketing specs of a new router model. The historical pivot from Wi-Fi 1 to current standards demonstrates that progress comes from solving the problem of shared medium access, not merely increasing transmission power or carrier frequencies. The one-user-at-a-time paradigm was shattered in 2014 with multi-user technologies, allowing simultaneous communication streams on different subchannels and spatial paths. This evolution proves that modern Wi-Fi is a software-defined coordination layer sitting atop physical radio waves rather than just a passive conduit for data packets moving from point A to point B. As you move forward, remember that the Internet itself remains a global network of networks distinct from the local wireless transport layer we call Wi-Fi. Wi-Fi serves as the last-mile radio conversation between your device and the router. What happens after that data leaves the range is entirely separate infrastructure managed by different protocols and providers. Confusing these two layers leads to poor troubleshooting habits, where you blame local hardware for global connectivity issues or assume a fast connection guarantees low latency regardless of network congestion levels. The engineering cost of this shared medium reality is significant but manageable with the right architectural mindset. You must accept that airtime fairness requires active scheduling and queuing strategies rather than passive transmission assumptions. By prioritizing coordination protocols over raw speed metrics, you build systems that remain stable under load while avoiding the pitfalls of saturation that plague poorly designed wireless deployments in dense environments today. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.